We start off this chapter with a reminder. We're still focused on carbon, and carbon can still only have 4 bonds. We talked about alkanes last chapter, where each of the bonds between carbons is a single bond. In this chapter, we'll focus on unsaturated hydrocarbons, arrangements where one of the bonds between the carbons is either a double bond, an alkene, or a triple bond, an alkyne. These are our first examples of functional groups. All of the reactions that we'll talk about in this chapter will occur only at the carbons that are part of these functional groups. So recognizing them will not only help with naming, but is essential for understanding the entire chapter. Alkenes are pretty important biologically. They show up in unsaturated fatty acids. They're also cyclic molecules with alternating double bonds called aromatics, which show up all over the place. Again, we don't see alkynes biologically, so we're going to talk about recognizing and naming them, but we won't focus as much on them. Alkenes have a double bond between 2 carbons, which means that 2 carbons will be bound to each other instead of being bound to hydrogens. As a result, the formula for a hydrocarbon with a single alkene is different from the formula for an alkane. Alkanes have the formula CnH2n plus 2, 2 hydrogens for every carbon plus 2 extra for the end carbons. Molecules with one alkene have the formula CnH2n, 2 hydrogens for every carbon. We'll use the relatively simple alkene, 1-butene, as an example so we can see why. If we look closely at the very first carbon on the left, we can see that it has 2 bonds indicated instead of 1, which means that instead of 3 hydrogens, it will have only 2. The next carbon has a double bond and a single bond for a total of 3 bonds, leaving room for just 1 hydrogen. Normally in the middle of an alkane, we'd have a CH2 group. That means we're missing a hydrogen on the first carbon and also the second, 1 missing on each carbon that's part of the alkene for a total of 2 missing. This will be the same every time we have a double bond. 2 hydrogens will go missing for each double bond. We can see the same thing happens if we have a ring. Since there are no end carbons, there aren't the 2 extra hydrogens for the ends. It also has 2 missing hydrogens. These 2 molecules are functional group isomers, isomers that have the different functional groups. Functional group isomers are a specific type of constitutional isomer. Again, isomers where the connectivity is different. We can look at the formula, and for every 2 hydrogens that are missing from the normal formula for an alkane, we know that there's either a double bond or a ring. We call the number of missing hydrogen pairs, sets of 2, the index of hydrogen deficiency, or IHD. The index of hydrogen deficiency is useful because it allows you to quickly identify the number of double bonds or rings in a formula. And so right away, if we see C4H8, we know that it's unsaturated and we need 1 double bond. In addition to functional group isomers, which are a type of constitutional isomer, we introduced 2 additional forms of constitutional isomers in this section. Positional and skeletal isomers are also both forms of constitutional isomers, that is, isomers that have different connectivity. Positional isomers just move a functional group along a carbon skeleton that's unchanged, as in the 2 alkenes that are currently shown. For example, the 1-butene was the simplest molecule for this formula that we came up with before, but we could easily move the alkene to the next carbon and have a 2-butene, which would be a positional isomer of 1-butene. Positional isomers will have different numbers for the functional group, so you see the 1-butene versus the 2-butene. Skeletal isomers, unlike positional isomers, actually move the connectivity between carbons, or the skeleton. This was the only way that we talked about constitutional isomerism before. So instead of having all 4 carbons in a row, A, B, C, D, we could have, like we see in 1-butene and 2-butene, we could have all 3 carbons in a row and the 4th one attached at carbon 2 instead of on the 3rd carbon, a 2-methylpropane. Because the carbon skeleton is arranged differently than 1-butene, 2-methylpropane is a skeletal isomer of 1-butene. Notice that isomers are relationships. 1-butene may be a positional isomer of 2-butene while also being a skeletal isomer of 2-methylpropene. It's not either of those things by itself. I'm a father because I have children and a husband because I'm married, but I'm not a husband to my children or a father to my wife. The relationships of people and of isomers are always relative. We have one final relationship specifically for 2-butene. Double bonds cannot rotate in the same way that single bonds can. They are constrained just like rings, making 2-butene actually refer to this unique molecule as well, a cis-trans isomer of the other 2-butene. In cases where double bonds have things locked in relative positions, they're given cis and trans labels, just like we can give those for rings. Imagine placing your pen down the middle of the double bond. One of these isomers will have both carbons on the same side, remember cis same side. The other will have carbons on opposite sides and be labeled as trans. Is the molecule on the left cis or trans? The left molecule is trans 2-butene, with the carbons falling on opposite sides of the double bond, making the right molecule cis 2-butene. Of the 3 molecules shown on the left, only 2-butene has this type of isomerism. If you place a pen over the double bond of 1-butene, for example, you'll notice that one carbon has hydrogens on both sides, making the sides identical to each other, and so cis-trans doesn't apply. Similarly, placing a pen over the double bond of 2-methylpropene will have one carbon that has hydrogens on both sides, and the other will have methyl groups on both sides, again, making the sides no different from one another. Suppose we had a question like, find all the isomers of C5H10. How might we try to do that? Thinking about the index of hydrogen deficiency and the types of isomers that are possible can be really helpful. First, what is the index of hydrogen deficiency for C5H10? C5H10 follows the form of twice as many hydrogens as carbons. We should have 2 extra for the ends, or CnH2n plus 2, if we had all single bonds and no double bonds or rings. Since we're missing 2 from that, we know that we have 1 double bond or 1 ring. We can start by drawing all the skeletons at work with a maximum of 1 ring. We won't worry about putting on the double bonds just yet. So we can start by putting all the carbons in a line. Just like when we were making only structural constitutional isomers of alkanes, we can take the N carbon and start to move it around. So if we have a chain of 4 carbons, we can only put the extra carbon on the second carbon and have it be a unique chain. 1 and 4 would give us a chain of 5 again, and 3 would give us the same skeleton as 2. So this is the only 4 carbon skeleton that we can have. We can also take 2 carbons off the end and put them both on the second carbon of propane. There are also cyclic skeletons that can work. One that's a cyclopentane, one that's a methyl cyclobutane, and 2 versions of dimethyl cyclopropane. At this point, we've identified all the possible skeletons for this formula. All of the cyclic molecules already have the right index of hydrogen deficiency, since they already show the 1 ring. But the linear molecules don't have the right formula as is. We can now take each of the linear skeletons and place 1 double bond someplace along the molecule to get all the possible positional isomers for each skeleton. So we first made a bunch of different skeletons, and now for each skeleton we're doing different positions. For the top skeleton, we can have a 1-pentene with the double bond between the first and second carbons, or a 2-pentene with the double bond between the second and third carbons. Any other positions of the double bond in this skeleton are duplicates. If we move the alkene further to the right, we just number from the other side instead. There are also a number of positional isomers for the 2-methylbutane skeleton that's shown in the second row. Again, the 2-methylbutane does not have the right formula, it's saturated, but it's a skeleton that we can place the double bonds on in different locations to find the correct isomers, like 2-methyl-1-butene, or 2-methyl-2-butene, or 3-methyl-1-butene. The final positional isomer gives a different number for the methyl because we number to keep the alkene as low as possible, but it's still the same skeleton. We'll talk about alkene numbering really soon. The third row has a 2,2-dimethylpropane, which is a possible skeleton for a 5-carbon molecule. However, it's not possible to put a double bond anywhere on this molecule without exceeding the carbons octet. So we can't make any molecules with the right formula from this skeleton. The last type of isomer that we'll look for are cis-trans isomers. These are only possible for the molecules with different things on both carbons of a double bond, like the 2-pentene, or with 2 groups coming off a ring, like 1,2-dimethyl cyclopropane. Chances are, if you drew an alkene that has cis-trans isomers, you do the trans isomer by instinct. It has the same zigzag shape that we normally draw for line angle structures. For the cis isomer, I usually draw the 4 carbons that define the cis bond first, the ones shaped kind of like a C, and then fill in the additional carbons in the line angle on the other side after I've drawn the cis. For the cis-trans in a ring, we probably didn't start out defining cis or trans at all, but it's usually easy to bold both bonds for cis and bold one and dash the other to indicate opposite sides for the trans molecule. Technically, this trans molecule has 2 different stereoisomers, the one on the right does anyway, like your right and left hand, but we don't go that far down into the rabbit hole in this class. As you can see, even for very short molecules, we can quickly have an enormous number of molecules with the same formula. In this class, I typically don't ask you to find every possible isomer on tests, but I do expect you to be able to find a few isomers of any formula. And I absolutely expect you to be able to identify whether molecules are isomers or not. As we've worked through some of the isomers, I've given names for the alkenes that we're working with. While you might not have understood the rules that generated those names, hopefully it was clear that alkene names are pretty similar in format to alkane names. In fact, we follow the exact same set of rules that we had for alkanes. It's just now we have a new functional group, and that affects a few of these steps. First, the highest priority group is probably going to be an alkene at this point. Second, because alkenes are our most important functional group at this point, both carbons of the alkene will always be part of whatever chain of carbons we choose as the main chain. Third, because we are no longer dealing with alkanes as the most important functional group, we change the suffix of these molecules from ane, ane for alkanes, to ene for alkenes. Fourth, the alkene will always get as low a number as possible, regardless of what the location of the side chain is. We'll always assign just one number for the alkene, even though there are 2 carbons that participate in that double bond. And it will always be assigned the lower of the 2 possible numbers. We can list that in a couple of different places and it'd be equally correct. We could list it directly before the ene suffix, as in but1-ene, or we could list it in front of the parent, as in 1-butene. The side chains are mostly the same as before, although now it's possible to get alkenes as a side chain as well. Finally, we'll sometimes need to use special descriptors cis or trans, just like we did for cycloalkanes. Let's apply these in action for a few simple alkenes. Let's start by doing the first 2 together, the first 2 in the column on the left. Remember, we always start by finding the longest chain that contains the functional group. And for alkenes, this means both carbons need to be part of the longest chain. In this case, the molecule can be numbered from left to right and have its maximum chain length of 5 carbons and also contain both carbons of the double bond. We number the alkene as 1, giving us a 1-pentene. Pent for 5, alkene because it's got a double bond, and 1 because the first carbon has the alkene on it. But it still has a 2-methyl side chain, so this is a 2-methyl 1-pentene. For most simple molecules, it's convenient to put the number for the functional group, like the 1 here, before the length part of the parent chain, as we did here. It's equally acceptable to put that number for the functional group directly before the suffix that indicates it, which in this case would give us 2-methyl pent1-ene. Either is acceptable. In more complex molecules, we will have suffixes that indicate 2 or more functional groups. In those cases, we'll actually need to use the second form so that we can clearly indicate which numbers go with which functional groups. We'll see more of that later. Before we decide that either of these names are complete, we do need to check to see if there are cis or trans isomers possible for this molecule. There are not, since the 1 carbon has hydrogens on both sides of the double bond. The next molecule down has 4 carbons in a line, with a double bond between the second and third. The molecule is then a 2-butene, but for 4, 2 because the lowest number of the carbons in the double bond is 2. Again, we must check to see if there are cis or trans versions possible for this molecule. In this case, the carbon attached to the alkene could be on either the same side or the opposite side. And since they're on opposite sides of each other, it is a trans 2-butene. Just like before, we can also put the number for the alkene directly before the suffix, like trans-but2-ene. Now pause and see if you can name the next 4 molecules before you continue. Remember that the alkenes always have to be a part of the main chain, even if a longer chain was possible without the alkene. The first molecule, or the next molecule rather, is a 2-methyl-2-pentene. It should be numbered left to right because it gives us lowest numbers, and it doesn't need a cis or trans because the 2-carbon of the alkene has methyl groups on both sides. We can also name it a 2-methyl-pent-2-ene. At the top of the second column, we have a chain of 6 possible from left to right, but would only give us one of the 2 alkene carbons. Instead, we need to number starting at the top carbon and then number toward the right, giving us a 2-ethyl-1-pentene, which we could also call a 2-ethyl-pent-1-ene. Cis or trans isn't necessary because one carbon has hydrogens on both sides. Again, notice that we named this a pentene even though there was a 6-carbon chain available because we had to have the double bond, both carbons, be part of that chain. The next molecule is a 1-butene, numbered from right to left to give the lowest number. It could also be called a but-1-ene. Finally, we have another 2-butene, but in this case, the carbons on carbon 2 and 3 are on the same side of the double bond as each other, making this a cis-2-butene, which could also be called cis-but-2-ene. The examples we've covered get at most of the simple cases. Let's look at a few special cases that might be a little bit more difficult to name, starting with alkenes and rings, cycloalkenes. But before we try to name the first molecule, what would the name for a 6-membered cycloalkane be? The same molecule without the double bond. If we had a 6-carbon cycloalkane, we'd name it a cyclohexane. Cyclo for the ring, hex for the 6 carbons, and ane because it only has carbon-carbon single bonds. So now we have a 6-carbon ring with a double bond, and the only thing we need to change is that ane, that indicated single bonds, to become ene to indicate a double bond. So we have cyclohexene. Again, cyclo for the ring, hex for the 6 carbons, and now ene for the alkene. Spelling is crucial in nomenclature because a single letter change gives us completely different molecules. We didn't include a number here because there's only one thing on the ring. As the highest priority group, the alkene automatically is numbered 1 and 2. The next molecule is again a cyclohexene, but now it has a side chain. Since the alkene is already 1 and 2, the lowest number that we could possibly give to the chlorine is 3 for a 3-chlorocyclohexene. Notice that we didn't include a number for the alkene. Because it's the only high priority group, we know that it's 1 and 2 without the numbers, but we still need the number for the chloro to indicate that it's right next to the alkene rather than further away. Now you try to name the last molecule. The final molecule is 4-bromocyclohexene. The alkene is positions 1 and 2, but this time we number counterclockwise because it gives us a lower number for the bromine. We might also encounter situations where there are multiple double bonds in the same molecule. This is the case, for example, with polyunsaturated fats, an essential part of the human diet. Just like when we had multiple side chains of the same type, we'll use the Latin prefixes di, tri, tetra, and so on. So this would be a diene because it has 2 alkenes. As with multiple side chains, we need a number for each alkene. So this molecule, which has 5 carbons and 2 alkenes, we'd number from the bottom right and up toward the left. The alkenes are at positions 1 and 3, making this a 1,3-dipentene. This is almost complete, except we always need to check to see if we need cis or trans labels. The 1-alkene doesn't need cis or trans labels, but the 3-alkene is the cis version, making this a cis-1,3-dipentene. We won't go through examples where multiple cis-trans labels are required in this class. Just like with monoalkenes, there are a few equivalent versions of the name, like cis-1,3-pentadiene and cis-penta-1,3-diene. Notice that when a Latin prefix like di or tri is used right in front of the alkene, ene, the A from the alkane, ane, is retained to make it easier to pronounce. Hence, we have cis-1,3-pentadiene instead of cis-1,3-pentadiene. There are also some situations where we might need to label alkenes as a side chain. This only occurs when the alkene occurs in a lower priority branch than the main chain. as is the case with this molecule. No matter what, we can only get 2 of the alkenes of the 3 to have both carbons as part of the main chain. So the main chain will be the 5-carbon chain, more or less top to bottom. Since the main chain is a diene, see if you can name just that main chain portion. The main chain is 1,4-dipentene, or 1,4-pentadiene, or even penta-1,4-diene. All are acceptable names for the same main chain. That leaves the pesky side chain with a 1 carbon and an alkene. But we know how to refer to a single carbon, meth, right? And we know how to refer to alkenes, we just use -ene. And to make it a side chain, we'll just drop the final E of ene and add -il to indicate that it's a side chain. So the whole side chain is a methenyl side chain, just like the methyl side chain, but now it's attached with a double bond. Our entire molecule's name is then 3-methenyl 1,4-pentadiene, or similar. If we had longer alkene side chains, we need to locate the double bond along that side chain, but that's outside the scope of this class. We'll only deal with methenyl side chains, no longer for this class. Here are a few more examples for you to try with some of the additional rules that we've just learned for rings, multiple alkenes, and alkenes as side chains. As a reminder, we typically would name the ring as the main chain, but if the alkene doesn't have both carbons in the ring, it's a side chain. Pause and give these a try. The first molecule is a cyclohexane. It can't be a cyclohexene because only one of the carbons of the double bond is part of the ring. So we name our 1-carbon alkene side chain methenyl, and the whole molecule then is a methenyl cyclohexane. The next molecule has 2 alkenes as part of the ring. So the alkene is part of the main chain in both cases. And because we now have 2 alkenes, this will be a dicyclohexene or a cyclohexadiene. Because we have to give a number for the second double bond to position it relative to the first, we must also give the number for the first alkene. We never give a di prefix without 2 numbers to go with them. The number should be 1 and 3 since both carbons 1 and 2 are part of the first alkene. The next one can only be as low as 3. And it doesn't matter in this case whether the numbers come at the beginning or directly in front of the alkene. Our final example is a 5-carbon chain. We number it from the left since that gives alkenes at 1 and 3 instead of 2 and 4. So the molecule is a 2,4-dimethyl 1,3-dipentene, or similar. In order to understand the physical properties of alkenes, like how readily they boil and whether they're soluble in water, we need to think about what types of intermolecular forces are present. Take a moment and look over the intermolecular forces that we reviewed last section and try to identify which intermolecular forces are the strongest for alkenes. London forces are the strongest intermolecular forces in alkenes because they don't have any electronegative atoms, just carbons and hydrogens. That means they'll vaporize very easily. They'll have low boiling points. However, just like in alkanes, increasing the number of carbons in an alkene will increase the chances for London interactions and increase the boiling points. Also, just like alkenes, London forces are too dissimilar to be appreciably soluble in water. And it only gets worse as carbons are added, so alkenes are not water soluble. In our last section, we looked at boiling point data to see how the branching affect the boiling point of alkanes. Did the boiling point increase or decrease as the chain was more branched? We see from the data that any type of branching ended up decreasing the boiling point because those molecules can no longer stack as closely, which also means that they couldn't act nearly as strongly. Cis and trans isomers of alkenes are locked into particular arrangements that can have a similar effect to branching. The trans arrangement, shown on the left, is easier to stack than the cis arrangement on the right. The trans carbons line up with each other, while the cis carbons get in the way of convenient interactions with the next carbon. So what would you expect to happen to the boiling point of an alkene as cis bonds are added? This chart shows the normal melting points of 18 carbon fatty acids based on the number of double bonds. Fatty acids are one of the main places biologically that we see double bonds. Does this chart show stronger or weaker interactions as cis double bonds, the only form that occurs naturally in fatty acids, are added to a molecule? Since as we add double bonds, the melting point is decreasing, this suggests that the strength of the interaction is weakening with more cis double bonds, allowing molecules to become liquid at much lower temperatures. As an aside, vegetable fatty acids tend to be much more unsaturated, that means more cis double bonds, which is why we commonly have liquid vegetable lipids like peanut, soy, or canola oil. Warm-blooded animals tend to have a higher portion of saturated fatty acids, which is why many animal fats are solid. We'll talk more about what this means nutritionally when we talk about lipids in the biochemistry section. Really, all of the reactions that we talk about with alkenes are versions of the same reaction. We call it an addition reaction. The electrons in the double bond pick up something positively charged like hydrogen, but are used in the process and the double bond is lost. To fill the octet of the other carbon, something with electrons, like the chlorine in this case, is bonded to the other carbon. As a result, we end up adding two pieces, one to each carbon of a double bond, and eliminating the double bond. There are 4 reactions in this section. They all follow these same rules. The only carbons that change are the alkene carbons. Each carbon gets one part of the other molecule, and the double bond goes away and becomes a single bond. And finally, the less electronegative atom, which for us is always going to be hydrogen, is always going to go to the less substituted carbon. Less substituted is just another way of saying the carbon that has fewer other carbons attached to it. So the hydrogen would go to a primary carbon over a secondary, for example. This rule for where hydrogen goes in these reactions is called Markovnikov's rule, after the scientist who first described it. It's worth mentioning that since when we typically draw the products as line angle structures, which don't include explicit hydrogens, the hydrogens that are added to make the product aren't always shown. So the product that's on the top would actually be displayed like this, only showing the carbon chain and the chlorine. It's fine with me if you want to show the hydrogen that was added, but you don't need to, and you wouldn't see it, say, on like a multiple choice question where you'd choose from a list of possible products. The first of these types of reactions is called a hydrogenation. We pronounce it hydrogenation, but notice that the name includes the word hydrogen, since we are adding a hydrogen molecule, H2. Each of the double bonded carbons gets a hydrogen and the double bond goes away. Again, while it's fine to think about the product as shown, hydrogens rarely are shown in line angle structures. And so it's far more likely that we'd see a product of hydrogenation look like this. It's the same carbon chain, just as an alkane instead of an alkene. Hydrogenations historically have played a huge role in food chemistry. Hydrogenated plant oils are commonly used to remove unsaturation. Remember, that's double bonds from vegetable oils to make them more shelf stable. But it's really hard to get this to happen completely in the complex mixtures of vegetable oils, and any incomplete or partial hydrogenation will form trans fatty acids byproducts. Trans fat doesn't need to be labeled until a serving has 0.5 grams of fat, which is actually quite a bit. The FDA actually even allows the food to be labeled as trans fat free with any amount less than 0.5 grams of trans fat. So, looking for the word hydrogenated or partially hydrogenated, which is far worse, in the ingredients list is a far better indicator if you're consuming trans fat in your diet. One more quick fun fact about trans fats. Cis fats can isomerize at very high temperatures, like greater than 140 degrees Celsius. Remember, 100 is boiling point for water. So high temperature cooking, like frying foods, can also lead to trans fat in your diet, even if you didn't add any trans fat in the first place. Hydrogenation does take place naturally in your body as part of both your central metabolism and the metabolism of fatty acids, but in each case the hydrogenation does not produce trans byproducts. Many textbooks will talk about palladium or platinum catalysts that are used to perform this reaction, but I'm most concerned about your eventual application of this reaction to our bodies, where we'll use the coenzyme FADH2 to accomplish this reaction instead. In biological examples, we can also move back from the alkane to the alkene, catalyzed by FAD. Moving back and forth between alkanes and alkenes is really common in biology and is a redox reaction. The alkane is the reduced form, and the alkene is the oxidized form. When alkanes are oxidized to alkenes, FAD is reduced to FADH2. The second type of reaction to alkenes is called a halogenation. Here the name is pronounced like you'd expect. It has the word halogen clearly in it. That's because we're adding halogen molecules to the alkene. Halogen atoms, that would be fluorine, chlorine, bromine, or iodine, are often generalized using the letter X, making the diatomic halogen molecule X2. Just like in hydrogenation, one part of the molecule adds to each carbon of the double bond, and the double bond doesn't go away. It doesn't matter what the halogen is, you get one atom on both sides. In line angle, there's less change from my glorious ball model diagram, but here's a line angle version just the same. Most molecular halogens aren't particularly good in high concentration, and they tend to be hard to remove completely from a food product, like, for instance, brominated vegetable oils. Brominated vegetable oils are actually outlawed in the European Union, but remain in use in the United States to help keep citrus flavor dissolved in citrus-flavored fizzy lifting drinks like Mountain Dew. There's little risk from low exposure to bromine that may occur with moderate consumption of carbonated beverages, but there is some concern that bromine may not be readily removed from your body, which means that the more and longer you consume brominated vegetable oil, like in Mountain Dew, the more likely it will become problematic. In the previous two reactions, the groups were the same on both sides. In hydration, which adds water to an alkene, the groups are hydrogen and an oxygen-hydrogen group, different on both sides. If you hydrate yourself, you add water to yourself. If you hydrate an alkene, you add water to an alkene. Because this molecule has two different groups, Markovnikov's rule tells us that the hydrogen will end up on the less substituted carbon, which in this case is the primary carbon on top. The other group, the OH, then needs to attach to the other carbon. Again, we don't draw out the hydrogens on a carbon in a line angle structure, so we're more likely to see the product shown like this. Hydration happens all the time in our metabolic processes. In the lab, we often catalyze this with a strong acid like sulfuric acid. In your body, this can typically be catalyzed by weak acids that are part of catalytic proteins called enzymes. Our final reaction, hydrohalogenation, is actually the archetype that we used for the first reaction we showed. In this reaction, a hydrogen, which is the source for the hydro part of the name, is added to the less substituted carbon, and a halogen is added to the other carbon of the double bond. Since the hydrogen isn't typically shown, the product looks only like the halogen is added to the more substituted carbon. It's easy to get tunnel vision as we learn reactions and think that we understand reactions really well because we show you the type of reaction that we just learned. To determine what type of reaction a molecule will go through, though, we need to be able to identify what functional groups might react and relate conditions to a specific functional group. In our section on alkanes, we learned about radical halogenations that occur on alkanes in the presence of light or heat and give us a mixture of products with just a single halogen. We can tell the difference between radical halogenations of alkanes and alkenes by identifying the functional group. Alkanes can't go through simple addition reactions with halogens because they don't have a double bond. And that's why we end up with this mixture of products instead of two bromines attached next to each other. Combustion also looks similar to an addition reaction, especially since it can happen just as easily for alkenes as it did for alkanes. Here we need to remember that oxygen is not a halogen, and it facilitates a combustion reaction rather than an addition reaction. Here are some more examples of the reactions of alkenes. In each case, we have the same alkene going through an addition reaction, so you just need to identify the pieces that will be added. Most of the pieces are pretty straightforward. From the top, two bromines, then a hydrogen and a chlorine, two hydrogens, and finally at the bottom we have a hydrogen and then an OH group, so two atoms being added as a single group. You also know that the only carbons that will be changed are the double bonded carbons. So now you just need to add the pieces to each side, being careful to add the hydrogen to the less substituted carbon if one of the pieces is hydrogen. And you need to make sure to get rid of the double bond. Pause and try to do these reactions yourself, and then we'll go over them. The first reaction is an alkene reacting with bromine. The two pieces are both bromines, so each carbon of the double bond gets a bromine, and the double bond turns to a single bond. The second reaction has a hydrogen and a chlorine adding across a bond that has a tertiary carbon on the left and a secondary carbon on the right. The hydrogen goes in the less substituted secondary carbon, which leaves the chlorine for the other atom. The third reaction adds hydrogens to both carbons of the double bond, which makes it look like the double bond just went away. It essentially did. The fourth reaction looks the same as the second, except that now the OH is added to the tertiary carbon instead of the Cl. Alkenes can also add to themselves through the same types of reactions, provided there's some sort of acid or Lewis acid catalyst, or light initiation of the reaction. Additions of these types give us many of the plastics we encounter day to day. The plastics industry has resin identification codes, those numbers inside of the recycling arrows, for 6 common types of plastic, and a 7th indicator as a catch-all for many other types of plastics. Of those 6 common plastic types, plastics 2 through 6 are all produced from the additions of alkenes. The reaction shown takes propylene, a trivial name for propene, and polymerizes it to polypropylene, a common plastic used for reusable food containers. Type 7 plastic includes many types of plastic, but most commonly is polycarbonate, the plastic in reusable water bottles like Nalgene water bottles. Type 7 also includes polylactic acid, which can be sourced from plant matter and is compostable in specialized facilities. Both polycarbonate and polylactic acid, along with type 1 plastic polyethylene terephthalate, are based on the ester functional group instead of polymerized alkenes. But there are many other plastics like ABS, the plastic of which most Lego are made, that are based on alkenes that also fall into type 7 category. So many of these plastics are very closely related to the chemistry that you've just learned. When plastics are recycled, they're not restored back to the individual molecules like polypropylene in most cases. Typically, they're sorted, shredded, rinsed, dried, and then the shreds are either ground further or melted into a new plastic. It's fairly difficult to get the waste streams very pure, and so recycled content in many cases can't be used in the same manner as before. Your plastic water bottle, for example, absolutely doesn't actually become a new plastic water bottle, but it may become a polyester shirt or a reusable grocery bag rather. In reality, very little plastic actually gets recycled. Less than 10% is estimated. And it's not just because things get thrown out into the trash, it's also because things that shouldn't go into the recycle, like food, end up contaminating the waste stream and needs to be put into the garbage anyway, even if it was in the right bin. And perhaps even more importantly, it's cheaper to make new plastics than to use old plastics. So the plastics get shipped overseas, historically to China, but at the time of this recording, mostly to Indonesia. They may be recycled there, but they often are dumped there instead, again, because it's so cheap to make new plastics. As Christians, we have a real responsibility to think about the impact of our buying and waste decisions on the rest of God's creation. While it might seem like plastic packaging can just be recycled and is therefore low impact, it actually has a really significant impact because it's probably shipped first to the coast and then shipped to Indonesia, where it may or may not actually be recycled. And there's some discussion among environmentalists and waste management professionals about whether it's actually lower impact to throw single-use plastics in the garbage. So am I telling you to never recycle? Absolutely not. But we do need to think about how we generate and deal with waste as a prioritization, rather than just thinking recycling is always a good thing. You've probably heard the mantra, reduce, reuse, recycle, the 3 R's. There's a Jack Johnson song that's very catchy. These are intended to be an ordered list. You make a much bigger waste impact if you don't consume anything at all, or if you use reusable containers than you can ever make an impact on reducing waste by recycling. This is actually part of a larger hierarchy that is used to prioritize waste management, the 5 R's. The most significant choice that you can make is to live simply. Be thankful for what you have and refuse what you don't need. The practice of thankfulness and refusing things we don't need is already a part of Christian practice, apart from the significant impact that our waste choices have on our brothers and sisters in Christ around the world and on the rest of creation. My goal here isn't to be prescriptive or judgmental about specific choices, But I do hope that taking a little bit of a magnifying glass to know about alkene-based polymers and how they're recycled or not gives you some additional context for what happens to single-use plastic waste and gives you a launching ground to think about what this means for your life as a faithful response to God's gifts.